Welcome and hello. This is a video tutorial on HEC HMS, and in this lesson, I'm going to be describing viewing simulation run results. All right, what I have on the screen here is my HMS. I have a basin that's already been loaded, as well as a meteorologic model and a controlled specification. And those three elements combined allow me to create a simulation run, which I've named May 1996. And I went ahead and ran that simulation. So if you're curious about the steps that I just described, watch any of the previous lessons, specifically the last two lessons, 59 and 60, where I created a simulation run and then computed the actual simulation run. All right, now we're on to viewing results. As you saw me do already, I just selected a simulation run and then clicked the run. There's other ways to run it as well. Now we have results that are saved for our basin model. In this lesson, I'm first going to describe viewing the global summary results, and then after that, summary results for individual hydrologic elements in the basin. All right, so the global summary results, there's three ways to view the same result data. The first is to go up to the results menu here and then click Global Summary Table. What we have in this summary table here is at the top, we have some general information about the simulation run itself, such as the start and end date time, which is dictated by the controlled specification here. We also have the time that the simulation was ran. So this is, at the time of this recording, it's October 2, 2024, as well as the basin model that's used, the meteorologic model that's used, and the controlled specification. And those are over here in the Watershed Explorer. Down below here in the main table of this dialog box is the data itself. Each row for one hydrologic element, that's the first column here, followed by columns for the drainage area, peak discharge, time of peak discharge, and then the volume in inches. I prefer to view the volume in acre feet, so I'll just click this radio button here in acre feet. Now, it's probably not too big a deal because inches could be multiplied by the basin area and then converted. But on certain dialog boxes, you'll see units of volume, and then it won't show the drainage area. So I just kind of like to keep it at acre feet. This table also allows you to select specific elements right now, but I have it set to all elements, and that's grayed out for me, as well as sorting options, either alphabetical or based on the Watershed Explorer, which is the same as the hydrologic order, where the bottommost record is closest to the outlet or the outlet itself. And then the next records up keep getting further and further away from the outlet. That should be the same ordering I have over here in the Watershed Explorer. Junction 2, Reach 1, Mahoney Creek Local. Junction 2, Reach 1, Mahoney Creek Local, and so on. I'm not showing it in this particular table, but if I had the sediment load computed for this subbasin, I would also see two additional columns on the far right, which I just don't have available in this simulation, but they are related to sediment load, and the column headings are sediment load in tons and then the sediment volume. So that was one way to view the global summary results. And I'm going to show you the other two ways, but I'm not going to describe the actual contents of the table because the table itself in this dialog box is the exact same data. All right, so what we already saw was going up to the results and then global summary table. The other way is to use the compute toolbar. This is the compute toolbar right here. This is where we selected our simulation run and we ran it. And then the next button over right here is view global summary table. If you don't see this toolbar, the compute toolbar, you can go up to view and then toolbars and then just click this one here, compute toolbar. So I'm not going to do it because that would turn it off for me, but go ahead and use that to view the compute toolbar. And if you click this button for view global summary table, here is the same table, except I have already selected a specific element. So let me unselect an element, click the global table, and here we go. I can go ahead and just do that as well. So if I wanted to select an individual element, now I can just change that filter to all elements, and that's what we saw originally. The third way to view the global summary results is over here in the Watershed Explorer. Typically, I'll like to have the components in view, the components tab here, but we also have a compute tab and a results tab. So the results tab is what we want to click. And then we have simulation runs directory. Underneath that, we have our simulation runs. I only have one simulation run. It's this one here labeled May 1996. And then down below that, I'll just do a single left click on this global summary icon, and boom, there's the same table. Next, it's time to talk about the individual elements and the results that we can view. Let me go to the Components tab here in the Watershed Explorer. And then for basin, I need to have a basin that's loaded in to my main view. So I can select the actual element, or I could select the element from the Watershed Explorer just as easily. The title bar right here of the basin model shows the selected basin. Right here it says Puxatawny, which is the name of the basin. And then after that, it says current run, May 1996. This is the selected simulation. So the results know exactly which basin and which simulation run to provide the results for when I make the clicks. If I change that simulation to none, then it disappears. There's just no label, and I can't actually access the results the way I normally would. Yeah, everything's grayed out. All right, let me go ahead and select that simulation run again. And just as before, there's multiple ways to view the data. So I'm going to view it the first way, explain the data, and then I'll mention the other ways. So the first way is the results menu. As we saw before, results menu, global summary table. Now right down here, we have element graph, element summary table, and element time series table. But right now it's grayed out because I need to actually make a selection of an individual hydrologic element so it knows which data to actually bring up. So let's go ahead and just click on Stump Creek. This is a sub-basin. And then I'll go up to results and element graph. Element summary table and element time series table are now all selectable. So here's the element graph. What I have here is a hyetograph showing rainfall data, and then below that, a hydrograph showing runoff data. This hyetograph here shows me in blue is the total precipitation, and then the red is the precipitation loss. In the bottom plot, the hydrograph here is the total outflow from that sub-basin, and then the base flow right here is this dashed line that's highlighted. The graph for every hydrologic element will at least include this hydrograph, which shows flow out of the element, but based on what type of hydrologic element it is, we'll get different other data. So in the case of a sub-basin, we see a hyetograph. Okay, let's go ahead and close that, and then go with Stump Creek still selected. I'm going to select element summary table. This is similar to the global table in the sense that we have the simulation run data at the top. So I'm not going to talk about that again, but down below we have computed results just for that selected hydrologic element, specifically the Stump Creek subbasin. So we have like the peak discharge, the time of peak discharge, and then a number of different volumes here for precipitation, loss, excess, and then direct runoff, base flow, and discharge. Right now it's showing in inches, and then I'm going to just change that to acre feet. So let's close that. And then let's see, next up is the last is the element time series table. So this time series data I'm about to bring up is basically the data that's used for the graph. So we saw this graph here. We saw rainfall depths, that's the hyetograph, and then flow rates or discharge values for the 6 days of the simulation here. And that's a flow rate. So the data for that is here in the element time series table. So what we have here is for every hour of the simulation, I'm sorry, every 15 minutes of the simulation, because that's the time interval of our controlled specification. We have our precipitation, we have our loss, and then the difference would be the excess that contributes to the overland flow runoff. Also, in the hydrograph values, here are our flow rates. We have the total flow, and then the base flow, and then the difference would be our direct flow. So these the excess in precipitation and direct flow in CFS would be the calculated values we don't actually see on the plot. But if I scroll down, they should become non-zero at the same time step. So let's just confirm that. Okay, so right about here, on April 30th at 7 a.m., we have the first non-zero values for excess precipitation and direct flow. Those are the different individual results we can see for the subbasin. If I go ahead and select other hydrologic elements like a reach or a junction, we'll see some different data. So real quick, let me just bring up the plot for the reach here. This is reach 1 that conveys flow from junction 1 to junction 2. What we see here in the plot here is the dashed line is the inflow, and then the solid blue line is the outflow. And then what we're noticing is that there is a lag. So let me pull this over to the side here. And the routing method in the components editor shows us that this is a lag routing method. There's other routing methods, of course. But if I click on the routing tab, I now see a 5-hour lag. So what I should see in the data table is an offset here of 5 hours. With the reach still selected, I'm going to go ahead and look at the summary element table. Again, similar with simulation run data at the top, and then computed run data here down below. But this is specific to that reach. And then if I click on results and element time series data, now I have each time step every 15 minutes. I see the inflow, and then I also see the outflow for the 6 days of simulation. Might be worth pointing out that the initial type is discharge equals inflow. So the original inflow is 140, and that's why the outflow equals 140 for the first 5 hours of the simulation, because that's the equal to the 300 minutes right here. And then once that 5 hours expires, we just have a 5-hour lag. So 139.6, 139.2 is the same as 139.6, 139.2, and so on. All right, so we looked at subbasins, we looked at reaches. Last is junctions. Here's junction 2. If I go results, element graph, we now see a hydrograph out of that junction 2, where this dashed line here refers to the incoming flow from reach 1, which would be from these two subbasins ultimately. And then this is from the subbasin right here, Mahoney Creek Local. And then the sum of those values would equal this solid blue line, which is the total outflow computed by HMS out of junction 2. And then this black line right here is observed flow, which is a separate time series data set that was not computed by HMS, but just loaded in externally for comparison purposes. And as you can see, this black line and the solid blue line here are very close to each other. So we will see some goodness of fit statistics data in just a moment. It's also worth mentioning that observed flow right here, this black line, has been loaded into junction 2. So if I click on junction 2 here in the basin map, and then over here in the components editor, if I click options, I now have this observed flow PNXP, which has been added to the model so that it will show up in the time series data when I look at the graph. Okay, so that was the graph for junction 2. Let's go ahead and check out the other summary table is right here. So the summary table is particularly interesting because of this observed flow gauge. Again, we have the simulation run data right here, and then we have some highlights for the outflow, such as the peak discharge, the time and date of the peak discharge, and then the volume, or in acre feet, it would be that value right there. Notice that this time and date of peak discharge is always to the nearest 15 minutes because that is the discretization or the smallest time interval in our control specification. So in reality, it would probably be 7.5 minutes of that value there. Down below, we have observed flow gauge, PNXP, with its own peak discharge and time to peak discharge. But we also have some statistical parameters down here, which indicate how close that observed flow is to the actual model outflow data for the duration of the 6-day simulation. This percent bias value is 1.39%, and this is just for my particular simulation and my model here. This is a parameter that quantifies how much simulated data deviates from the observed data. So a 0% would be perfect, but then anything under 10% would be very good. Under 15% is good. Under 25% is acceptable. And then if it's greater than 25%, then that's unacceptable. Those are just my generic standards, but your specific company or organization may have specific standards on what is required for percent bias. This percent bias is also a absolute value. So 1.39% is just as good as negative 1.39%. 40% is just as bad as positive 40%. If this percentage is greater than 0, like it is now, 1.39%, that means the model underestimates the observed data. And then if it's less than 0%, then the model overestimates the observed data. There's also this Nash-Sutcliffe efficiency value. And a perfect value here would be 1. So 0.95 is very good. Anything greater than 0.5 is pretty good and acceptable. And then 0 would just be kind of average based on the observed data. And if it's less than 0, it's very bad. So anything less than half is probably not good enough. And then lastly, there's this RMSE, standard deviation, root mean squared, error normalized by standard deviation of the observations. Okay, so that was it for junctions. Let's see, results, element time series for the junction. Again, this is the same data that we saw that defines the flow rates that we saw in the graph. And then just as a quick refresher, this is the graph that data is used to define. Okay, so we looked at subbasins, we looked at the reach as well as junctions. There are some other examples. Obviously, there's other hydrologic element types such as reservoirs, diversions, sources, and sinks. I'm not going to cover that in this video, but it would be the same way to view the results of a simulation. You go up to results and then select the graph, summary table, or time series table. There is a way to view multiple elements at the same time. So if I wanted to hold down control and select, say, all my subbasin hydrologic elements, then they're highlighted all at the same time here in the basin model, and they're all highlighted in the Watershed Explorer as well. So what I could do is with them all highlighted, I can come up to results and select, say, element graph. What that'll do is it'll bring up the element graph for all three of these hydrologic elements, these subbasins. I'm going to go ahead and close them. And then same way with the other options, I can open up all three summary tables at the same time. And I don't have to select them using the basin map. I can hold down control and select them by just single left click over here in the Watershed Explorer. Same thing. We can also open up the time series data. Now, what I don't like is that it opens them up in different tables and different plots. I can't combine the view in one single window, but at the end of the lesson, I will show you a solution to that. We don't have to even select we can select all the elements in the entire basin, and then let's just, for fun, open up all the graphs. So I just opened up 6 or 7 graphs there, so you don't have to, but that's how that works. So far, I've only showed you one way to view the results from individual hydrologic elements, which was by going up to this results menu and then selecting graph, summary table, or time series table. There are 4 other ways to get the same data. The first, or I should say the next way, is by right-clicking on the hydrologic element in the basin map and then coming down here to view results and then selecting graph, summary table, or time series table. Notice that right here it says May 1996. This is just another reminder of which simulation run I'm getting the data from. So just to confirm, here is that plot for the graph for Stump Creek Subbasin. And then here is the summary table. And then right click, here is the time series table. Another way to get data from an individual hydrologic element, this will be the third way, is to click on one of these buttons up here in the compute toolbar. So if I don't have any item selected, then those options are grayed out. But if I select one, we'll go with junction 1 this time, then I've got the options to select the graph, the summary table, and the time series data. So here's the graph. This is for junction 1 now. And then the second one is the summary table, and then here is the time series table. So that's all the user's manual has to say about viewing results for individual hydrologic elements, but there is a couple other ways. Over here in the Watershed Explorer, if you click on the Results tab, we now have a directory for simulation runs, and then below that, all of our simulation runs. Now, we only have one simulation run in this particular project, so if I expand that, I see global summary. We saw that already, but now I have individual icons here for each hydrologic element, such as the subbasins, the junctions, and our reach. So go ahead and then click the plus to expand. You might not have a plus icon, and if you don't, just click on the text and then the plus icon appears, or the minus icon appears if it's expanded out already to collapse. For a subbasin, let's stick with Stump Creek. I'll go ahead and expand that. Now I see the graph, the summary table, and the time series table, just like we saw in the buttons, and then all the other options. So here's the Stump Creek graph, summary table, and time series table. These other results here are shown: outflow, cumulative outflow, precipitation. They're showing up down here in the component editor location. And this is DSS data that's been saved during the computation. These time series data sets are saved in a DSS file that's specified at the compute tab. So if I click on compute and then I select the simulation run, we have this output DSS file right here. And this is May 1996.dss, which leads me to the fifth and final way to view the results, and that is from the DSS file itself using DSSVue. Here is my directory. Here's the project directory. Our project's called Lesson 61, so your project would probably be called something else. But if you click into that project directory, we see all the normal files and folders we expect to see, like basin states, data, forecast, frequency, maps, GIS. And then when you create a project, there's also a default.dss file that's labeled with the name of the project .dss. So for me, it's this one right here. It's lesson 61.dss. I don't think this DSS file has any data in it right now, but whenever you create a simulation run and run it, then the output as it's defined also gets saved to a DSS file, which by default will be in this project directory. Specifically, in my case, we're looking at the May 1996.dss file right here. And this is the DSS file I'm interested in to view the results using the DSSVue HEC application. There's also the third and final DSS file in this directory is time series data, and this was just imported into my project when I imported a simulation run. So we can look at that too, I suppose. But this is not the output data. This is used for precipitation gauge data and that observed flow time series data set. Okay, I got DSSVue up on the screen here. And what I first want to do is just open those DSS files. So I'm going to navigate to, yeah, this is exactly where I want to be. Let's start with the lesson 61 DSS file. I believe there's no records in here. Okay, just wanted to confirm that. In DSSVue, the individual DSS files do show up on tabs along the top at this location. So here's the first file. I'm just going to leave that open, and then let's open up the next file, May1996.dss. So this is where I believe the results are stored for my May 96 simulation. And then here is the data. And just out of curiosity, before we dig into these results, I want to open up the time series DSS. Open. Okay, right. This is what I expected to see. We have precipitation gauge data at 3 locations plus the observed flow at P and XP. So we don't need to deal with that right there. Let's go back to our results. Here we have the results from our simulation run. So in part B, we have the meteorologic model, such as the EB Mahoning Creek subbasin. We have junction 1, junction 2. Here's the other Mahoning Creek local subbasin, and then Reach 1 and Stump Creek. I can already tell by observation that these subbasins have more data than either the reaches or the junctions, and that's fine. We also have the date range here in part D, which is the 6-day simulation, as well as part C, which actually describes what the data is. So for instance, if I wanted to see, what were we looking at? How about the Stump Creek subbasin outflow? I'll go down to Stump Creek, and then here is the flow. So here is the plot, and this is just for that one subbasin. But one thing that we couldn't easily do in HMS, at least I couldn't easily do it with my limited knowledge, is to combine the data for multiple hydrologic elements in the same plot or the same window. So using DSSVue, that's not a problem. We'll just go ahead and select the flow from those 3 subbasins. Now, an easy way to do that is to filter. I'm just going to type in flow here, and it should work. I'm going to click search over on the right. Cool. Now, only part C equals flow records are showing in my results. So I can just go ahead and hold down control for the records I want to select for the 3 subbasins and then click the plot icon. Very cool. So what we have here is the 3 different subbasins. So the yellow right here, this is Stump Creek, and then EB Mahoning Creek subbasin is in green, and then the Mahoning Creek outflow is shown here in red. So there's a lot of different ways to view the data. I could actually highlight all the flow records. Yeah, that's fine. Let's just see what this looks like. We now have 6 records. So the purple is Stump Creek. So if you add that to the EB Mahoning Creek subbasin, those two combined would equal the outflow from junction 1, which is red, right? So green plus purple equals red. And then let's see, blue is the Mahoning Creek local subbasin outflow. So that's right here. So I guess the red and the blue would equal the yellow, which is the junction 2 outflow, but there's also that 5-hour lag in the reach. So I'm not going to try to figure that out right now. And I don't need to. I could actually come up to File and Tabulate. This is the same thing that would happen if I click the Tabulate button right here. I'm seeing all the numbers that are used to populate that graph. So DSSVue is really the Swiss Army knife, sort of the Excel of the HEC programs, where we have a little bit more freedom and flexibility to manipulate the data, and that's particularly helpful when we're looking at results and we can't actually get the results that we want using the built-in tools that are part of HEC HMS. Well, that was it for this lesson. We talked about viewing different basin model results. We looked at global results and then the results for individual hydrologic elements, specifically the graph, the summary table, and the element time series table.